Hello everyone, my name is Chidambram AL and I am currently pursuing a Masters in Construction Engineering and Management at CEPT University under the Faculty of Technology. I am here to present my direct research paper under the guidance of Dr. Devanshu Pandit and my co-guide Mrs. Aurav Agarwal. My research topic is Machine Learning-based classification of bid risk in Indian public construction tenders using historical and competition-driven features. Before I get into the slides, let me give you a very quick sense of what this research is really about. In government construction projects, when tender is published, the contractor decides whether to bid and at what price. Sometimes the contractor bids may below the government estimated cost. We call it an aggressive bidding. Sometimes a bid comes in above the estimated cost that we call as an above estimate bidding. Both of these are risky outcomes for the project. This research is about predicting these two types of risk before the bids are even submitted using machine learning and historical tender data. That is a core idea, and I will walk you through every steps of how that was done. This slide covers the complete foundation of the research: the aim, problem, gap, needs, and the approach. The aim of this research is to develop a machine learning based classification framework that predicts the probability of two types of bid risk: aggressive bidding, where the winning bid price is below 15% of government estimate cost for the project, and the excess estimate bidding, where the winning bid comes in excess the estimate of the project cost. The goal is to enable early stage data driven decision making in construction procurement. The research problem is straightforward. In Indian government construction tenders, nobody systematically identifies bid risk before the bids are opened. There is no tool, no system, or no process that flags whether the particular tender is likely to attract aggressive or excess estimate bids. This is the gap this research fills. Looking at the research gap, most existing studies focus on predicting the bid price or cost estimate, not on classifying the bid risk. They do not capture competition intensity or historical bidding behavior. And there is a very limited research using structured government tender data set from India for this purpose. There are four clear needs driving this study: the absence of bid risk assessment in the current L1 system, the limitation of traditional estimation methods, the uncertainty in competitive bidding environments, and the lack of data-driven decision tools. On the right side of this slide is a key shift this research proposed from deterministic estimation to predictive analytics. In traditional process, a contractor receives tender details, spends multiple days preparing the BOQ, doing detailed price analysis, preparing documents, getting internal approvals, and then submitting. This can take up to 9 to 10 days per tender. With a risk-based approach, the contractor first runs the model, gets the risk classification, and decides whether to bid at all. Only if the tender looks feasible does the contractor invest time in detailed estimation. This saves approximately 4 to 6 days per non-feasible tender. The literature review was structured across 7 sections, from government procurement and contractor behavior to classification methods and the research gap. This slide covers the first and most important section. On public procurement in India, the study of Pati in 2009 showed that the current L1 system, which selects the lowest bidder, relies entirely on price-based selection. This encourages the contractors to cut margins, submit aggressive bids, and creates a financial risk in project execution. The winner's cruise concept from Chen in 1990 is critical to understanding this problem. In a sealed bid action, which is exactly how Indian government tenders work, contractor bid without knowing what their competitors are quoting. The contractor who wins is often the one who underestimates the project cost most. This leads to cost overrun, project delays, and contractual disputes. It's a systematic, predictable pattern, and the predictability is exactly what this research shows. On the right side, the Pareto chart from Syed in 2023 confirms that out of all the variable influencing the bidding behavior, only a small number of key drivers, competition intensity, financial condition, and market variability, account for the majority of bid risk. This justifies using a feature based, data driven classification approach rather than trying to model every possible variable. Most traditional estimation methods do not prioritize the variables this way, which is why the procedure inconsistent results shows. This slide covers three more sections: feature engineering, classification models, and the limitation of traditional bidding models. Feature engineering is the process of converting the raw tender data into meaningful behavior data-driven indicators. Studies by Zhang in 2025 and Ibercom in 2024 confirms that when raw data is transformed into risk-sensitive features such as historical bid ratios, competition intensity index, and the distance to metro, classification accuracy improves significantly. The shape chart here confirms this with the project size and the construction worker showing very high predictive power when properly engineered. On the right side, the limitation of traditional bidding models, Fireman, Gates, game theory, and regression are clear. All of them make simplified assumptions, both contractor behavior and focus on predicting the bid price rather than the bid risk. Machine learning models, on the other hand, learn directly from the historical data, capture nonlinear relationships, and produce probability-based risk outputs. This is the core argument for the approach used in this research. Traditional models miss real bidding risk, and machine learning captures with true data-driven pattern learning. The next is research methodology. The research follows a structured machine learning classification framework. The complete methodology flow is shown on this slide, starting from the aim and the conceptual framework through the literature review, data collection, data cleaning, and feature engineering, ML model development, model evaluation, and finally the bit scenes tool output. The data collection involves 500 tenders above 100 crore rupees collected from the e-public procurement portal for financial years 2024 to 2026. Originally 500 tenders, but 496 after data cleaning were analyzed using 79 engineered features, AUC-based feature selection, and an 80:20 ratio training to testing split. The model used are elastic regression, random forest, and XGBoost. Evaluation metrics include accuracy, AUC, ROC, confusion matrix, precision, recall, and F1 score. The three outputs of this research are high accuracy, risk prediction, aggressive and excess estimate bid precision, support, and optimized top 15 feature model. Feature engineering transformed raw tender data into structured predictive indicators through two stages: initial process attribute structuring on this slide and the behavioral feature derivation on the next. Six initial bifurcations were performed. Sector classification defined five infrastructure sectors, with the built environment dominating at 36% and other balanced between 14 to 19%, preventing sector bias. Geographic classification across four regions showed West India at 32.4% and other regions between 20 to 25%, capturing region-dependent bidding behavior influenced by market condition and contractor availability. Project duration was dominated by medium-term projects at 42.6% and long-term at 33.6%, reflecting common government project timelines. Project size was divided into five equal bands, from very low, less than or equal to 128 crores, to very high, greater than 512 crores, each contributing 20%, ensuring balanced scale representation. Client-wise bid deviation showed central government and PSU projects with the highest discount at minus 11.21%, indicating aggressive bidding, while state government minus 0.20% and state PSU minus 1.32% remained near estimate, and ULB projects showed above estimate bidding at plus 1.51% due to lower competition. Market competition was distributed across low 33%, moderate 40%, and high 26.4% categories, capturing varied competitive bidding conditions. In the detailed feature engineering stage, 79 engineered features were developed from 500 tenders, reduced to 496 after cleaning using the bid discount ratio or BDR as a center metric. BDR is the estimated cost divided by the winning bid. It standardized the bidding behavior across the projects of different size and sectors. Two classification targets are defined. Aggressive bidding has target 1 when BDR is less than 0.85, meaning the winning bid price is more than 15% below the estimate. Above the estimate as target 2 when BDR is greater than 1. Features were evaluated using AUC, point visual correlation, and direction. A Python-based framework was used for accurate pairwise AUC computation. Excel was tried initially, but could not perform reliable pairwise comparison. The top-ranked feature is ANC cost tier BDR with an average AUC of 0.924. Importantly, its correlation is only 0.02, very low, yet its AUC is 0.92. This proves that ASU captures nonlinear discrimination ability far better than correlation alone. This was a key methodological insight. Relying on correlation could have incorrectly ranked this feature as unimportant. Multiple metrics are essential for robust future evaluation. The BDR distribution shows most bit cluster around BDR equal to 1, while bits below 0.85 and above 1 represent the target risk categories. The spread from 0.6 to 1.4 confirms significant variability for classification. The dataset was split into 18:20 ratio with 396 centers for training and 100 for testing. Four feature subsets, top 10, 15, 30, and 50, were evaluated with top 15 selected as the best performance complexity balance. The top 15 model achieved 97% accuracy and AAC of 0.99 for aggressive bidding and 95.6% accuracy with AAC of 0.99 for excess estimate with very few misclassifications in the confusion matrix. Although all feature subsets achieved AAC equal to 0.99, the top 15 model provided the best F1 score balance while additional features showed diminishing returns and slight noise increase. Gini index feature importance showed aggressive bidding was dominated by historical BDR cost tier 0.66 and a contract type 0.17, contributing over 80% of predictions, where above estimate bidding depends on multiple factors including cost tier, contract type, client sector, expected bidders, and geographic indicators, justifying the use of random forest for excess estimate and a random boosting for aggressive bidding. The model was first tested in Google Colab using a real-world scenario. A mega NHA highway project in Bihar, 280 kilometers from the nearest metro, under an item rate contract for a central agency. The model outputs 82.5% aggressive bid risk, classified as a high risk, and 27.4% estimate risk as a low risk. This makes complete sense. National contractors compete aggressively for mega NHI contracts, driving bids down below the estimate. But because competition is intense and the contractors are pricing to win, bids stay within the estimate. The heat map analysis was done to show the risk patterns across state cost layer combinations using controlled inputs. The result is very clear. Aggressive bid risk is highest for small and mega cost layers, ranging from 0.84 to 0.90 across states, and a medium and large cost layer shows very low risk, just 0.02 to 0.06. This confirms cost layer as a dominant driver. Small projects attract aggressive local competition. Mega projects attract strategic aggressive bidding from large contractors. The excess estimate heat map is not presented. It produces uniform outputs value due to a feature pipeline inconsistency and is excluded to maintain analytical reliability. This is acknowledged limitations. The BitSyn tool translates the trained model into a real-time browser-based prediction tool built using HTML and JavaScript and deployed on GitHub page. It is freely accessible from any browser with no installations or login required. The user enters just 8 key inputs, and the tool internally reconstructs all 15 engineered features and immediately outputs a risk probability, the risk level grade, and recommended actions. It makes machine learning outputs accessible to procurement officers and the contractors with zero technical background. This slide shows the BitSync tool validation on the real mega project scenario. A linear transport project in Jammu and Kashmir 730 kilometers from the nearest metro by NHAA on the item rate contract. The tool outputs aggressive bid risk 1%, not aggressive. X estimate risk 99%, level 3 major overrun. This is completely logical. At 730 kilometers from the nearest metro, in difficult and remote location, very few contractors are willing to bid. Those who do must price conservatively because execution risk is extremely high. No aggressive bidding happens, and the cost is very likely to exceed the estimate. The tool then translates it into four specific actionable procurement strategies. First, the review engineer's estimate to ensure the cost baseline is accurate before tender is published. Second, pre-approve 15% contingency budget to protect against financial uncertainty. Third, include the price variation clause in the contract to handle inflation and cost escalation over time. Fourth, prepare revision documentation in advance so budget changes can proceed quickly. The model performance conforms AAC of 0.998 and 0.995, accuracy of 98% and 95%, F1 of 0.93 and 0.90, and critically the train test AAC gap is less than 0.001, confirming no overfitting and strong generalization to unseen data. The future explanation shows why the model predicted high risk exit risk. Cost their PDR of 1.02 signals historical overrun tendency. Distance to metro of 730 km indicates remote location with low competition, and the remote indicator flag confirms high execution complexity. Very every prediction is fully explainable to real measurable feature. This is not a black box. It is a transparent, interpretable decision support system. Conclusion for this research. On model performance, both model achieve AAC of 0.99, accuracy of 98%, and F1 score up to 0.94. The train test AAC gap is less than 0.01, confirming strong generalization. These models are reliable, consistent, and validated on real data. On optimal model selection, the top 15 feature set gives the best balance between performance and simplicity. Gradient boosting is selected for aggressive bit classification due to its high F1 and strong nonlinear learning. Random forest is selected for excess estimate due to its stability and better control over false positive. Future importance true. Gini index makes every prediction interpretable. We know exactly which fuses are driving each output and why. On the real world tool, BitSim takes 8 user inputs, reconstructs 15 engineered features, and instantly generates risk probabilities with level grading and recommended action. It is free browser-based and requires known technical expertise. It bridges the gap between machine learning research and actual procurement practice. The complete journey is from data to model to prediction to decision. This research enables smart, transparent, and risk-aware procurement in Indian public construction. Thank you all for your attention and time.